All right, here are solutions to the log equations worksheet from class today. Just a whole bunch of log equations with either logs or exponents in them, and we're trying to solve for x. For this first one here, you notice there's just a single variable, this x here. So essentially we want to kind of isolate it, get it all by itself. So you got all sorts of numbers to kind of deal with and things to get rid of, essentially. So we'll start by adding 4 to both sides of the equation. So I got log base 2 of 3x plus 2 plus 5 all divided by 2 equals 4. And then if you multiply both sides by 2, you get that the log base 2 of 3x plus 2 plus 5 equals 8. So now I guess I could subtract 3 from both sides of the equation. Maybe I'll hop up here. And that gets me to the log base 2 of 3x plus 2 equals 3. Subtract 5 from both sides of the equation. Hopefully that's what I said. And you get here. And now is where things change a little bit. Either you memorize how to change a log equation into an exponential equation, or better yet, you do 2 to both sides of the equation. For most of the worksheet, I won't be writing this step, but for the first time I do it, maybe I'll actually write it out to show you what's going on here mathematically. If this equals this, then 2 raised up to this equals 2 raised up to this. But the advantage of having 2 raised up to the log base 2 of something is that you're composing together inverse functions. Essentially, what ends up happening is over here, this whole thing just simplifies down to 3x plus 2. So I got 3x plus 2 equals whatever 2 to the third power is. Turns out it's 8. So now I can subtract 2 from both sides and get 3x equals 6, and therefore x equals 2. I guess similar logic in this next one. We just have a single x here. We want to isolate it. Okay, let's get rid of this 9. Multiply both sides by 9. That gives me 4 raised up to the log base 3 of 5x plus 1 plus 2 equals 18. Now if I subtract 2 from both sides of the equation, I get 4 raised up to the log base 3 of 5x plus 1 equals 16. And you might think 4 raised up to the log base 3 of something, you might think you can simplify that like we did here when we had 2 raised up to the log base 2. But in fact you can't. What allowed us to do it over here was the fact that the bases were the same. The base in the exponential function was the same and the base in the logarithmic function, which makes them inverse functions of each other. That's not what's going on here because I got a 4 and I got a 3. So what am I going to do? Well, I could take the log base 4 of both sides of the equation. Maybe I'll write that out again the first time I do it, and then I won't going forward. If all this stuff equals this, then the log base 4 of all this stuff get my parentheses right, equals the log base 4 of 16. Well, the log base 4 of 16 is just 2, because the log base 4 of 16 is asking you what power do you got to raise 4 to make it equal 16, and 4 squared is 16. Over here, the log base 4 of 4 raised up to stuff is just equal to that stuff. Either because, again, this same logic where I'm composing together a function and its inverse function, or using your third log rule, you can take this whole exponent here and bring it down in front of the log base 4 of 4, which is just equal to 1. At any rate, regardless of how you think about it, you should get that this is the log base 3 of 5x plus 1. And so now I can solve this. Getting closer and closer to getting at this x here, I guess I'd want to get rid of the log base 3, so I'll do 3 to both sides of the equation. And as I promised, I'm not going to keep writing out that step, so I'll just say 5x plus 1 equals 3 squared. And since 3 squared is 9, I got 5x plus 1 equals 9. I wonder if that's what I meant. Maybe I wanted that to be minus 1, so this would be 10. But whatever, it's not. Subtract 1 from both sides of the equation, you get 5x equals 8. Divided by 5, you get x equals 8 fifths. I probably meant for this to be 5x minus 1. So all this would be the same. And then you'd get to this step, and you'd add 1 to both sides of the equation. The answer would be a nice whole number. But whatever, I guess there's no problem with fractions, so I'll go ahead and call that good. All right, next one. This problem, I think, is a step up in difficulty level. The challenge here is that I have multiple x's floating around. I got a 2x up here in the exponent and a 3x plus 2 over here in the exponent. A couple options in terms of how you could attack this. One way is you could take the log base 3 of both sides of the equation straight off the bat. Maybe I'll even write a couple ways. Option 1. You take the log base 3 of both sides. And over here on the right-hand side, I got the log base 3 of 3 raised up to some power. That simplifies really nicely. That simplifies down to just 3x plus 2. Unfortunately, I don't get quite so lucky over here because of this coefficient, this 5. But I can deal with it. I can use a log rule to say I got the log base 3 of 5 plus the log base 3 of 3 raised up to the 2x power. And then I can do the same simplification that I did over here on this log base 3 of 3 to the 2x term. I get the log base 3 of 5 plus 2x equals 3x plus 2. And so now I can solve for x, maybe up here. Let's see, I'd probably subtract 2x from both sides and then subtract 2 from both sides. And that would give me the log base 3 of 5 minus 2 is equal to x, which is a perfectly good answer, and I'd leave my answer just like that. Since I'm here, let me show you another way you could attack this problem. Before you go taking the log of both sides of the equation, you could divide both sides of the equation by 3 raised up to the 2x power. That would give you something that looks like this. You'd have 5 on one side of the equation, and on the other side of the equation, you'd have 3 raised up to the 3x plus 2 power divided by 3 to the 2x power. And the nice thing about this is when you have a quotient of exponents and they have the same base, you can just subtract what's up in the exponent. So I could say this is 3x, maybe I'll write out a step, 3x plus 2 minus the 2x. But now I combine like terms. 3x minus 2x just leaves me with 1x. So I get 5 is equal to 3 to the x power, 3 to the x plus 2 power. Now I can solve for x by taking the log base 3 of both sides and subtracting 2. I get x is equal to the log base 3 of 5 minus 2. Throw parentheses in there to make it clear that I'm just taking the log of the 5, not of the negative 2. So there's a couple different ways you could have done that problem. This one, D, you're like, whoa, he messed up. He put the same problem on twice. Actually, no, these are slightly different. In D, the bases are not the same. I got a 3 here and a 2 here. So option 2 won't work. You're forced to go with option 1. But we can do it. We can take the log. What base do you use? You want to use base 3 or base 2? Because you'll pick the right base for one side, but it'll be the wrong base for the other side. It really doesn't matter what base you take. To prove that to you, I'll take the natural log, because why not? Now I can't cancel stuff out, but I can still use my log rules. So I got the natural log of 5 plus the natural log of 3 raised up to the 2x power is equal to the natural log of 2 raised up to the 3x plus 2 power. So applying my third log rule, I can bring all those exponents down in front. Get natural log of 5 plus 2x times the natural log of 3 equals 3x plus 2 times the natural log of 2. The advantage of this form is, even though it looks ugly, it's really just a linear equation at this point. Get all the terms with x's in them on the same side of the equation, either combine like terms or factor, and solve for x. These parentheses get in the way of that process, so fine, get rid of them. Natural log of 5 plus 2x times the natural log of 3. I'm going to write that as 2 natural log 3 times x. Whatever. And then I have 3x plus 2 times the natural log of 2, so I'm going to distribute that natural log of 2 through, and that'll give me 3 natural log of 2 x plus 2 natural log of 2. And so this term's got an x in it, and this term's got an x in it. So let's move those all to one side of the equation. I got 2 natural log of 3 times x minus 3 natural log of 2 times x is equal to 2 natural log of 2 minus the natural log of 5. Okay, both of these terms have an x in them, so I can factor out an x. I got x times 2 natural log of 3 minus 3 natural log of 2 is equal to 2 natural log of 2 minus the natural log of 5. So I could divide and get x equals 2 natural log of 2 minus the natural log of 5 divided by 2 natural log of 3 minus 3 natural log of 2. Perfectly good answer. You can leave it like this, just FYI. I could apply my second log rule, and that would make this make it the natural log of 2 squared, but 2 squared is 4. So I could have the natural log of 4 minus the natural log of 5, which I could apply my second log rule to, and make it the natural log of 4/5. Same logic on the bottom here. I can make this the natural log of 3 squared is 9, and 2 cubed is 8. So if I felt like I could write things like this, I don't really know why you'd feel like it. Either answer is totally fine. I'm going to call that good. All right, part E here. Couple options in terms of how you do this. I think probably easiest would be to attack it just like you did part D. You might be able to get kind of clever and come up with some other ways to do it, but I think it's going to more or less be that same problem. Well, it's not entirely true. Okay, let me show you another way you could do this if you felt like it. Sure, maybe that's instructive. So instead of 3 raised up to the 2 times x power, I could write that as 3 squared raised up to the x power. Why the hell would you do that? Why would you think to do that? Those are all very fair questions. I don't know that you would think to do that, but you can, because if I started you out here, you'd say, oh, I got an exponent raised up to an exponent, so I multiply those two together and get 3 to the 2x power. Okay, fine, I guess I see that, but I'm still not sure where you're going. All right, well, 3 squared is 9, so I got 2 times 9x is equal to 12 times 6x. And so now I can maybe get all the terms with an x in the exponent on one side of the equation. So 9 to the x power over 6 to the x power equals 12 divided by 2. So I divided both sides by 6 to the x power and divided both sides by 2. Well, 9 to the x divided by 6 to the x turns out to be 9/6, aka 3/2, to the x power. 12/2 is just 6. So that gives me this equation, which I can solve if I take a log of both sides, maybe a natural log, whatever log you want. Let's just take log, why not? The log of 3/2 to the x power equals the log of 6. So using my third log rule, I can make this x times the log of 3/2 equals the log of 6. So x is equal to the log of 6 divided by the log of 3/2, which I think is how I'm going to leave my answer. There's more you could do. Should I do more? No, I don't want to do more. I'm going to call that my answer and move on. This video is long enough already. This one, I don't know if I'm being funny here or what the hell I'm doing with this problem, but it's not as hard as it looks. Impossible, right? It's actually not that bad at all. Just start kind of chipping away from the outside in. I want to get rid of this log base 2. So do 2 to both sides of the equation. If you do 2 to both sides of the equation, the 2 and the log 2 will cancel out. So I'd be left with just the log base 3 of the log base 4 of 3 times 5 to the 4x minus 10 minus 11 equals 2 to the 0 power. But wait a minute, 2 to the 0 power is just 1. Okay, so I have this whole thing equals 1. Now I'd like to get rid of this log base 3. I'll do 3 to both sides of the equation. Gives me the log base 4 of 3 times 5 to the 4x minus 10 power minus 11 is equal to, this equals 1, and 3 to the first power is just 3. And then repeat. Get rid of this log base 4 by doing 4 to both sides of the equation. Now I got 3 times 5 to the 4x minus 10 minus 11 equals 4 to the third power. 4 to the third power, 4 times 4 is 16, times 4 again is 64. So I have 3 times 5 to the 4x minus 10 minus 11 equals 64. And I can add 11 to both sides of the equation and get 3 times 5 to the 4x minus 10 equals 75. And at this stage, it's a little bit more manageable. I want to get at this x here, so I'm going to have to take a log. But before I take a log, if I took a log right now, having this product would be kind of annoying. So what I'm going to do is divide both sides by 3 and make this 5 to the 4x minus 10 power equals 75. Now I could take a log. Whoa, 75. How about 25? I divided both sides by 3. 75 divided by 3 is 25. Now I can take the log base 5 of both sides and get 4x minus 10 is equal to the log base 5 of 25. But the log base 5 of 25 is asking you what power must 5 be raised to make it 25? And the answer is 2. So I got 4x minus 10 equals 2, aka 4x equals 12, aka x equals 3. How am I doing on time here? That's pretty long. I'll stop this video here and do page 2 in another recording.